Howdy statisticians, here's just another quick follow-up video where now we're going to be looking at a two-sample Z interval for the difference between two proportions. A Z interval, now we're going to be making an interval that's for making an estimate that about the difference between the population proportions we find in two populations. So in our previous video, we were talking about an example here where, say we had a population of males and we had a population of females, and we were trying to observe in these two populations, is there any difference in the proportion of people that are left-handed, right? So let's say P has to do with the proportion who are left-handed, right? Left-handed. And so we said, is the proportion of left-handed people amongst males different from the proportion of females? And we did a significance test, and we ended up failing to reject the null hypothesis. We did not have significant evidence that there is a difference here. We got a massive p-value based on a sample. So today we're going to just look at a quick video where we're going to make an estimate. Our goal is to not just conclude, do we have evidence about whether or not there is a difference or not, but we're going to say, can we make an estimate for to try to figure out what is the difference? What is the difference, right? Between the proportion of males and females that are left-handed, right? And so if you recall, we had a sample where we had the number of males that were left-handed was 12 out of 100. Our sample size, again, was 100. And then amongst the females, we found that there was it was 17 out of 115, right? And so based on this, we ended up failing to reject the null hypothesis that we didn't necessarily find evidence of a significant difference. But now again, we're going to try to make a confidence interval for the actual difference between these two proportions. What really is, our question is, what is PM minus PF, right? What does this actually equal? And here, order actually matters, because if I'm trying to say what's the difference, it's if I do PF minus PM or PM minus PF, I'm going to get change the signs of my values here. It's not that deep, but in this case, I don't know what that difference is, so I'm going to try to estimate it. How will I estimate it? Well, I'm going to estimate it based on my sample values. So in my sample, I found I'm going to use whatever I got in my first sample minus whatever I got in my second sample as my key estimate, and then I need to get to that a margin of error. So I'm going to add and subtract to that a critical value, in this case it'll be a z-score, times a standard error formula for that's based on my two samples, the standard error for P1 minus P2. Now, we actually saw in our last video what that standard error formula would kind of look like based on the standard error for a sampling distribution. So this standard error, the standard error of P hat 1 minus P hat 2 is going to equal a big square root, and it's going to be whatever I got in my first sample minus whatever, 1 minus whatever I got in my first sample over the sample size in my first sample, plus my second sample proportion minus 1 minus that, there we go, blah, 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 and 2, and go like this. Now, one key thing to point out here is that remember when we did the significance test and we had a test statistic, we had to use this whole pooled proportion thing where we combined our two samples together to get a better estimate to use for our standard error. But the only reason that worked is because we began with this null hypothesis that P1 was equal to P2, or in that case, the proportion of males is equal to the proportion of females. So I could just combine the samples together to get a better estimate. In this case, I begin with no such null hypothesis. I'm not assuming that there's no difference. I'm just trying to estimate what the difference is. So I'm actually going to use the separate P hat 1 and P hat 2 for each of the two elements for calculating our standard error formulas here, right? So that's cool. Let's plug this in. Now, of course, I need to decide on some type of level of confidence. And so I don't know what kind of level of confidence do you guys want to use. How about 95%? That's pretty much what we use by default almost. How am I spelling confidence? Confidence, right? 95%. Let's do that. So if I was to do this by hand, I would say the difference between these two proportions would be my estimate for what the difference is. And actually, when we were doing our significance test, we already found that difference was -0. I forgot that 0 last time. That was sad. 0.278 26. That's very, very thorough. Plus or minus. Now, what's the z-score for 95%? It hasn't changed. It's still, what is it? You guys remember? 1.96, right? And then, of course, we'll multiply that by a big old standard error formula. Let me get this guy. So that would end up being what? That would be the 0.12 times 0.88 over 100 plus, we'll add to that, what was 17 out of 115? I'm just going to actually do it that way. I'm going to do 17 out of 115 times, what was that again? I forgot. Let's see, what's 115 minus 17? I forget. It's 98. I should remember that. 98 over 115, and I'll divide that whole thing by 115, and I'll get a thing. Now, this is going to be a little bit different than my last standard error. That's no problem. Let me stick it in the calculator. Again, that was 0.12 times 0.88 divided by 100 plus 17 out of 115 times 98 divided by 115 divided by 115. Oh my gosh, it's crazy. And I get here 0.4638. So that's my standard error, 0.4638. I'll multiply that by 1.96 to get the margin of error, right? And so then I'll take my negative 0.027826, and I'll add to it that margin of error, and I have that that right side, and then I'll do the exact same thing, but I'll subtract it. Nothing like copy and paste. And there we go. Here is my estimate for for the actual difference in the percentage of left-handed and right-handed people amongst males and females. And it's actually a massive interval, right? Let me get another sheet of paper here because I'm a little bit out of space. And so my confidence interval is going to be from negative 0.1187 all the way up to positive 0.0631, right? And 3.1, right? And so in this case, it really should be no surprise that we failed to reject the null hypothesis, because this is our estimate for what the actual difference is between the proportion of males, the proportion of females that are left-handed. It's something that's 0 is in this interval, so it makes sense that we would fail to reject that there is no difference in the proportion of males and females that are left-handed. Just like we saw in the other guide, though, of course, there was a much quicker way to make a confidence interval. Doing all of this by hand is cumbersome, and you can make errors, even though it shows the depth of your understanding. There's a lot of labor in here. So if you go into your calculator and you go to, in this case, a 2-prop z-int, it's a 2-proportion z-interval, put in all the information. Notice my calculator remembered everything I typed in before, 95% confidence, hit calculate, and shazam. There you go, right there. There's your confidence interval, right? Mathematically, nothing that deep, especially if you can just do a 2-prop z-int to get this whole job done. And why spend all the time and effort that we did here. The only key thing, what's the key takeaway? When the only way that this works, of course, is we'll have to check large counts again. And beautiful that the large counts condition for a 2-sample z-interval will be exactly the same. It's that large counts condition that allowed us to use the normal distribution z-score in making our confidence interval. Nothing deep there. So make sure you check your large counts. Make sure that you're actually using p-hat here, p-hat1 and p-hat2, and not throwing in the pool proportion. The pool proportion is just for the test statistic. Guys, easy stuff here. I hope you have a beautiful day. Happy calculating. Catch you on the flip side.